This is acidic!
Quite so. Why is this a problem?
I got some in my blood. My blood should become acidic. Then I should die. How long do I have left?
I see. You won't die. I dealt with the same problem years ago as a young man. After a long time searching my soul in chemistry textbooks, I came upon the reason why we don't die after getting lemons on cuts.
Really? How did you know?
Get these buffers you seek to understand!
Buffers?
They have the ability to prevent your blood from becoming acidic. Amazingly, they also prevent your blood from becoming basic, like your outfit.
My outfit isn't basic. It's $200.
It is clear you have much to learn. We need to leave to visit the chemistry building. Everybody out now. I have this room reserved. Anyways, as I mentioned earlier, buffers have the ability to resist changes in pH when an acid or base is added to a buffer solution. A simple example is a mixture of acetic acid and its conjugate base, sodium acetate, in water. If we add a small amount of a strong base, such as sodium hydroxide, to the solution, the acid will neutralize the sodium hydroxide according to the following reaction.
Wait. So you're telling me I can dump as much base as I want into the buffer?
No. However, small amounts of base or acid in a buffer solution will not alter the solution's pH very much. But before we get ahead of ourselves, we need to understand how to find the pH of a buffer solution based on the concentrations of acid and conjugate base. To do this, we need to use a little bit of math. Starting with the equation for the dissociation of acetic acid and water, we can write Ka as this. We can rearrange this equation to have the hydronium ion concentration on the left. Because pH is simply the negative log of the hydronium ion concentration in solution, we can take the negative log of both sides of the equation and expand it. Now, if we remember the definition for pKa, we can finally write the equation for calculating the pH of the buffer solution as this. This can also be generalized to any buffer solution using a weak acid and its conjugate base. This formula is known as the Henderson-Hasselbalch equation.
Yeah, that final equation looked really easy. Very lazy.
I know, isn't it wonderful? Let's go through an example to make sure we know what's going on. Let's pretend we made a buffer solution with 0.1 molar acetic acid and 0.1 molar sodium acetate. To calculate the pH of this buffer solution, all we need is a pKa of acetic acid, which is around 4.74. We just plug in 4.74 for pKa and replace base and acid in our equation with 0.1. Since the ratio of 0.1 over 0.1 is 1, and the log of 1 is 0, we can easily see that the pH of this solution will be 4.74.
Wow, that's almost cheating, it's so easy! But, could you do one where the pH doesn't equal the pKa?
Of course! Now assume we started with 0.1 molar acetic acid and 0.2 molar sodium acetate. We can write the equation for pH to be this, and calculating the log portion of the formula, we find that the pH will be around 5.04.
This is fascinating. However, I don't understand what this has to do with lemons. You're telling me that this solution of acetic acid and sodium acetate will resist a change in pH?
Absolutely. Let's assume again that we start with 50 milliliters of 0.1 molar acetic acid and 50 milliliters of 0.1 molar sodium acetate. As we calculated in the previous example, the pH will be 4.74, and at this point we have a buffer. If you add base, for example 0.1 molar NaOH, the change of pH will be very slow. Also notice that if we add acid, such as 0.1 molar hydrochloric acid, the pH change will also be very small. As you can see in the figure, as small amounts of acid or base are added, the pH changes very little. This is the buffer region of your solution.
So this is how my blood doesn't become more acidic when I put lemon juice in it.
Not exactly. Your blood uses a buffer of carbonic acid and bicarbonate anion. However, the principle behind resisting changes in pH is the same.
But at some point, the pH changes really quickly. Why is that?
At some point, in this example, once 50 milliliters of 0.1 molar NaOH is added, the acid in solution is completely neutralized. This causes a drastic change in pH, which shows our buffer solution is now exhausted and cannot resist changes in pH anymore.
Look, these graphs and equations are great and all, but can you actually prove that this happens?
Yes, I can prove it, but we'll have to leave and go to the lab. Do you remember what concentrations of acid and base we used in the example that had a pH of 4.74?
Yes, it was 0.1 molar acetic acid and 0.1 molar sodium acetate.
Great! Now create a 100 milliliter solution of that. Now could you test the pH of that and tell me the value you get?
Looks like I get exactly 4.74, just like you predicted earlier.
Fantastic! Now take out your lemon. Now, cut it open. Squeeze the lemon into the buffer solution. Now squeeze the lemon into this beaker of 100 milliliters of deionized water. Test the pH of both of them.
I see. So the pH of the buffer solution didn't change much at all, while the pH of the pure water dropped significantly.
What are you doing in here, old man? Get up!